Hello students, welcome to EPG Pathshala. I am Dr. Aranya Bhattacharjee from the School of Physical Sciences, Jawaharlal Nehru University, New Delhi. Well, today we are going to discuss about the module Diamagnetism and Paramagnetism of Atoms 1 from the paper Solid State Physics. So students, let us see what we are going to learn in this module today. Well, the first point is learn about the quantum theory of magnetic moments of atoms. Understand what the Hund's rule are, and then apply the Hund's rule to evaluate the total angular momentum of an atom or an ion. And finally, learn about the origin of magnetic behavior of these systems. So students, in most of the solids, the magnetic response is dominated by permanent dipoles. Well, you know what dipoles are. The origin of permanent and induced magnetic dipoles can be explained on the basis of quantum mechanics. So try to understand this, students, that magnetism cannot be explained by classical physics. We have to take the help of quantum mechanics to understand the origin of permanent and induced magnetic dipoles. So from classical considerations, in thermal equilibrium, there can be no magnetic moment even in the presence of applied magnetic field. Isn't it surprising? So consequently, magnetism is purely a quantum effect. The origin of the two types of magnetism, namely the diamagnetism and paramagnetism, lies in induced and permanent magnetic moments. Okay, so now let's talk about an aim. So the aim is how to describe the effect of an external magnetic field on the behavior of a solid substance. So you see, we are talking about the behavior of a solid on application of an external magnetic field. Now, in the limit of weak fields, okay, weak fields, basically what we're talking about is weak magnetic fields. And remember, I mean, the response of a solid to weak fields and strong fields are quite different. So here, in the limit of weak fields, the response of the solid to the external magnetic field is measured by the susceptibility. Susceptibility is equal to the magnetization divided by the external field. Or, you know, you talk about H or B, so you can write it in terms of B field also, but you have to multiply this by the permeability of free space. So nu naught, the magnetization vector M divided by B vector. Further, magnetic field and the magnetization density is decomposed in Fourier components, and as a result the susceptibility, which is the response function, becomes wave vector and frequency dependent. So this wave vector and frequency dependence is basically coming in because we are decomposing it into Fourier components. They are working now in Fourier space, not in real space but in Fourier space. So in Fourier space the susceptibility then becomes a function of the vector q, that is a wave vector, and the frequency component. So we are going to do is now start with the quantum theory of magnetic moment of atoms. Now according to the Bose quantization condition, the magnetic moment is quantized according to the following formula. So the magnetic moment is equal to E h cross divided by 2m multiplied by the vector small l. And as you can see that the quantity in the bracket has been denoted by nu b. So what exactly is nu b? Is the Bohr magneton, and the value of the Bohr magneton is displayed on the slide. So it's very important that you know what exactly is the Bohr magneton and what's its value. And also the vector small l is the orbital angular momentum of the electron. So now continuing with the quantum theory of magnetic moment of atoms, the spin magnetic moment is given by the following expression, where the small g naught is the electronic g factor and the value of the electronic g factor is 2.0023 as shown in the slide. And what is the s? S is the spin quantum number, which is half. So this expression that you see in the slide is the spin quantum number. So now let's talk about the quantum theory of magnetic moments of atoms. So as I already said that it's only the quantum theory which can help us to understand the magnetism in solids. So how to determine the total angular momentum of many electron, atom or ion? Okay, because you see, when we are talking about magnetism, we are dealing with magnetic moments, we are dealing with angular momentums, spins. So these things have to be taken into account. So vector addition of the individual orbital and the spin angular momentum gives rise to two different kinds of coupling. One is called the LS coupling, the other is called the JJ coupling. So LS coupling of course is known by another name, the Russell-Saunders coupling also. Now, how to determine total angular momentum of many electron, atom or ions? This is a very important question. In fact, one of the very fundamental questions before you actually start to study magnetism. For many electron, atom or ions, we need to determine this total angular momentum. So starting from this, we do a vector addition of the individual orbital and spin angular momentum. The LS coupling is called the Russell-Saunders coupling, and the JJ coupling is basically the coupling between the J. So we have the JJ coupling and the LS coupling. So LS coupling is also known as the Russell-Saunders coupling. And whatever we are talking about right now, we will be also showing in a figure which will be very clear. So now we have this figure 1, which actually demonstrates the vector addition of these angular momenta which we were talking about. So the orbital quantum numbers of the individual electrons are vectorially added to get the net orbital angular momentum. So as you can see from this figure A, 1A, you have two vectors L1 and L2, and a simple vector addition gives rise to the capital L. And in a similar manner, you see that you have got two spins S1 and S2, which we add vectorially, and then we get the sum total in a vector way, the capital S. And on the right hand side, you get to see the figure 1B, where you see that the vector addition of the L and S components are shown. So you see that in figure 1A, the L1 L2 addition, capital L, is again shown slightly near the bottom of the B part, and on the right hand side on the top shows you exactly the vector addition of S1 and S2, and then you get to see the vector addition of capital L and capital S, which gives rise to J. So this is basically the LS coupling forming the vector J. So now what I had told in the previous slide regarding showing in the figure, I also show this mathematically, the LS coupling, the Russell-Saunders coupling, and the vector addition of that. So as you can see that the net orbital angular momentum is equal to h cross summation over the small l's, where I index is basically it runs over all the atoms or the ions. So the orbital quantum number of individual electrons are added vectorially, added to get the net orbital angular momentum. Now also, as you can see from here, you see the spin quantum number of individual electrons are added vectorially to the net spin angular momentum. H cross capital S is equal to H cross summation over all the small s, where again I is the sum over all the electrons. So now what happens, as again I showed you in the figure also 1b, that after you get the total L and S, this is capital L and capital S, you have to add them, and that will give you the total vector j, the total angular momentum, which is written as h cross j is equal to h cross L plus h cross capital S. So, in the LS coupling, which is also called the Russell-Saunders coupling, now since the only conserved vector is j, okay, so remember the j is the conserved vector. The magnetic field causes L plus twice of S to persist about the fixed vector j. This is the LS coupling. The existence of a permanent magnetic moment is essential to the magnetic behavior of a system. Now, nu can be estimated by calculating L and S of individual atoms or ions of the system. And L and S, you know, like this capital L and capital S is basically the L is capital L is a summation over all the small L's, and capital S is the summation over all the small s. So, of the electrons, you know, like as many as electrons are there in these atoms and ions, the summation goes according to that. This is done according to Pauli's exclusion principle and Hund's rule, which describes how electrons are assigned to various states. So, two very important things, Pauli's exclusion principle and Hund's rule. You have to sort of understand these two and make use of it. The Hund's rule. First rule is the electron spins are added so as to get the maximum possible S as permitted by Pauli principle. The second rule, the orbital momenta are added so as to get the maximum value of capital L, and at the same time it should be consistent with capital S that was determined according to the first rule. So, you see the first and the second go together. So, if you get the first rule right, the second rule has to follow at the same time, it has to satisfy the first rule. And finally, the third rule, the total angular momentum for less than half filled shell is J equal to mod of L minus S, and for more than half filled shells is J equal to mod of L plus S. This is very important. So, less than half filled, mod of L minus S, and more than half filled, it is L plus S. So, we will be applying these to some examples, and you should remember this third rule also. Now, what we do here is to study and understand the use of quantum numbers in the theory of atoms. And of course, this is very essential before we actually proceed ahead. First, the principal quantum number n determines the energy of the orbit, and remember that n is equal to 1, 2, 3 are only the integers. The corresponding electronic shells are called capital K, L, M, N shells. The angular momentum of the orbit is determined by the quantum numbers small l equal to 0, 1, 2 till small n minus 1. The total angular momentum associated with a given value of L is equal to h cross into L plus 1 j under root. So, these electrons with state L equal to 0, 1, 2, 3 are called sp, d, f, g electrons respectively. So, this implies that electrons in an s state always have 0 angular momentum, that is small l equal to 0, and thus the magnetic moment is 0. A very important result. The possible components of the angular momentum along, say, the direction of an external magnetic field is determined by the magnetic quantum number m, where m is restricted to the following values. M, L is, we have a subscript L here, which basically tells you that m depends upon L, is equal to L minus 1 till 0, then minus L minus 1 minus L. So, basically what you get to see is that ML is varying between plus L and minus L. An electron in the p state has L equal to 1. So, we again, you know, like start taking an example. And for this L equal to 1, what are the possible values of ml? That is, from our prescription that we had given earlier in the slide 14, is -1, 0 and +1. The possible components of angular momentum along the direction of the magnetic field are h cross, 0 and -h cross. As a result, the possible magnetic moment components along the direction of an applied magnetic field are minus E into h cross divided by 2m, 0 and plus E h cross divided by 2m. Finally, the electron has an angular momentum known as spin. The angular momentum components of the spin along an external field direction are only 2, plus minus h cross by 2. Thus, the spin quantum number is simply plus minus half. Now, here we will give some examples, and first we consider the case of the chromium 3 plus ion. Now, chromium 3 plus ion is a transition metal ion of the iron group. So, its 3D shell is partially filled and contains 3 electrons. That is, for complete occupancy, it is short of 7 electrons. For the chromium ion, L equal to 2, so that Ml is equal to 2, 1, 0, -1 and -2, characterizing 5 different degenerate orbitals. So, degenerate orbital basically means that they have the same energy. Now, let us apply the Hund's second rule to get maximum values of S and L. The electrons are filled in the orbital as we see here below, and up arrow is indicating that the electron is pointing up with the quantum value of ms is equal to plus half. So, ml is equal to 2, 1, 0, -1, -2, as we have seen in the third sentence of this slide. Now, we have got 3 electrons. Okay, this again we see that we had mentioned this in the second sentence of this slide. There were 3 electrons and you have to place them in these shells. So, starting from the first shell, that is ml equal to 2, I place 1 electron pointing up, the second electron ml equal to 1 pointing up, and the third electron ml equal to 0 pointing. Now, the total L is equal to sum over the mLs, which very simply is equal to 3. That is the sum taken over occupied orbitals. And also at the same time, we have the capital S, which is the sum over ms, which is equal to 3 by 2, because they are all pointing up. So, half plus half plus half, giving it 3 by 2. Now, since the shell is less than half filled in accordance with the Hund's third rule, capital J would be mod of L minus S, which is equal to 3 by 2. The energy states of any atom is denoted by, let us say, mxa, where capital M is 2s plus 1, called the multiplicity, and A equal to J is the total angular momentum quantum number. Now, since L is equal to 3, x equal to F, therefore, the ground state of chromium 3 plus is 4F 3 by 2. So, this basically tells us that it shows a paramagnetic behavior due to the non-vanishing total angular momentum. Now, consider the case of HO3 plus ion. Its 4F shell is partially filled and contains 10 electrons and represented by 4F10. And also remember that this is basically the electronic configuration of the incomplete shell. That is what we have given here. For the shell, L is equal to 3, hence the filling of electrons in orbitals is as follows. But remember that each time you have L, you should also write down ml. So, I have written down here ml is equal to 3, 2, 1, 0, -1, -2 and -3, which is characterizing the 7 different degenerate orbitals. So, now we apply the Hund's second rule also, but before that, the important factor here is that whenever you try to find out or try to solve the magnetic properties of any kind of ions, it's repeatedly I am saying that it is very important that first you proceed according to the Hund's rule. That is very important. So, continuing, that electrons are filled in the orbitals as shown below. I mean, this is again like is a repetition of what we did in the previous case also, but now this is slightly more complex because you have got now more electrons. Earlier you had 3 electrons, now you have got 10 electrons. And as you can see from here that ml is 3, 2, 1, 0, minus 1, minus 2 and minus 3, and accordingly now you have to sort of fill up these states. So what we do is that we start with the up spin and fill them all up. Okay, so you got 10 electrons. So you place each of these up spin electrons in these levels, starting from 3, 2, 1, 0, minus 1, minus 2, minus 3. Now these are how many states? 7. So why are you left with now 3 electrons with down spin? So what we do is that now we start again from the first ml equal to 3 level and fill it completely with the down spin, 2 down spin and 1 down spin. So what you can see from here is that the 3, 2 and 1 level, they are paired. The electrons in these 3 levels are paired, while in the rest 4, 0, minus 1, minus 2 and minus 3, they are unpaired, with only contains only the up spin electrons. Now continuing with the HO3 plus ion. So as before, L is equal to summation over ml, which is basically 6 here, and S is equal to summation over ms, which is equal to 2 here. Since the shell is more than half filled in accordance with the Hund's third rule, so you see it's very important, less than half filled, more than half filled, there are 2 different cases. So J will be equal to mod of L plus S, which is equal to 8. The energy states of any atom is denoted by again mxa, where m is equal to 2s plus 1, called the multiplicity. Repeating, A equal to J is the total angular momentum quantum number. Now since L equal to 3, x equal to I, therefore the ground state of HO3 plus I is 5Is. It shows paramagnetic behavior due to the non-vanishing total angular momentum. Now the third case that we are considering here is Mn3 plus ion. Now its 3D shell is partially filled and contains 4 electrons. That is, for complete occupancy, it is short of 1 electron for half fill. It's for the chromium ion then L equal to 2, so that Ml equal to 2, 1, 0, minus 1 and minus 2, characterizing 5 different degenerate orbitals. Now we apply the Hund's second rule to get a maximum value of S and L, and electrons are filled in the orbital S, again in the 4 electrons. So each of the up spin electrons, they are first occupying 2, 1, 0, minus 1, and minus 2 is left vacant. Okay, so this is the case here for the Mn3 plus ions, and also remember that it's the 3D shell. So again, as before, capital L is sum over ml, which is 2, and capital S is sum over ms, which is again equal to 2. Now since the shell is less than half filled, in accordance with the Hund's third rule, we have J mod of L minus S is equal to 0. This is a very interesting case. Now, as usual, the notation, that is mxa for this specific case, as you can see from here, would be simply 5d0. Okay, so and why is it so? That see, so A is basically equal to J, where J we have found out is equal to 0, and mxa, so m is equal to 2s plus 1, so s equal to 2, and then this means that m equal to 5. Okay, and again it shows a second order paramagnetic behavior, and it has no net magnetic moment. This is very interesting, as you can see that it is very different from the previous 2 cases that we had dealt with. That is, Mn3 plus has got no net angular momentum, J equal to 0, we have found out. So this is similar to the case of ions having completely filled shells. These type of ions are like Mn3 plus, chromium 2 plus. They show second order paramagnetism. So finally, in this module we have studied many things. So these things are listed like this. The first, Bohr's quantization condition. Second, origin of permanent and induced magnetic dipoles, which can be explained on the basis of quantum theory. Difference between LS coupling, JJ coupling, and also we have learned that what exactly is the Hund's rule. Now also the use of quantum numbers in the theory of atoms we have learned. 3 rules to calculate the total net angular momentum of an ion or an atom, and hence calculate the magnetic moment that we have learned. And we have taken as an illustration 3 examples of chromium 3 plus, HO 3 plus, Mn 3 plus ions to find their term symbols and how they show paramagnetic behavior. So, I hope that you have learned some things from this which you can apply to the studying the further aspects of magnetism of solids. Thank you very much.